Hello, my name is Maddie Stone, and this is Kylie McRoberts. Thank you all for making it back from lunch. And so hopefully it's exciting, keep you awake post-lunch, and we will dive into the trends that we've seen of Android mobile malware in the first half of 2018, and then really deep dive into 4 of the most impactful families. What do they do? Why are they impactful? What techniques do they use? And things like that. So first off, as I said, my name is Maddie Stone. I am a reverse engineer on Google Play Protect, or the Android security team at Google, and I have about 5 years of experience before that doing hardware and firmware exploitation.
Hi, and I'm Kylie McRoberts. So I'm a program manager on Google Play Protect under Android security team. And essentially, if you think my accent sounds weird for an American, it's because I'm actually Australian. So let's not confuse that. All right, so as Maddie said, we're going to be diving into some of the trends that we've seen in the first half of 2017, and then we're going to be looking at some of the technical details of some of the key families that we've seen impacting those trends. But before we do, I'm just going to take 1 or 2 minutes just to quickly tell you where that data is coming from, so we're all on the same page. And it's from Google Play Protect. So we'll quickly run over what it is and what the scope is. First, though, we're going to be referring a lot to potentially harmful applications, or PHA. So for us, PHA is defined as an app that could put the user, their data, or their device at risk. So in many ways, our definition of PHA is fairly in line with sort of the traditional definitions of mobile malware that most people use. A key difference is that for us, PHA is defined by specific categories, and I'll go into what they are later. But the main takeaway for you guys is that those categories define the scope of the type of PHA or malware that we'll be discussing today in the trends. So as I said, where do we get that data from? It comes from Google Play Protect. This slide says lots of things, but the main thing you guys need to know is that Google Play Protect essentially scans devices which have it enabled, and what we're doing is looking for evidence of PHA. So where we find PHA, we show a user a warning to let them know that that exists on their device, or in the cases of particularly harmful PHAs, we can actually automatically block or uninstall that app for the user. Now, because GPP, or Google Play Protect, is covering over 2 billion devices in the ecosystem, this really helps us to get some good insights into PHA trends over the years. And it's that device base which we're going to be using today to pull out the trends. So I mentioned for us, PHA is defined by specific categories, and those categories are listed here on the slide. So if you're interested in the definitions of each one, they are publicly available. You can Google them, ironically, and have a look at what we define for each category. But as you can see, some of them are fairly common and be familiar to everyone, like ransomware, phishing, and Trojans. One set of categories that I'd call out that might be less familiar are related to mobile billing fraud. So essentially those are applications that charge the user in an intentionally misleading way, basically tricking the user into having charges against them. And we divide those, that particular category into 3. So you can see them listed here as SMS fraud, toll fraud, and call fraud. We also have some categories up here which essentially can either modify or disable the inbuilt security features in Android. And for that reason, we define them at Google as PHA. Now, we do understand that for some users, those particular apps perform functions that they actually want, and they actually want the applications. But nonetheless, we define it as PHA so that we can then show a warning to users, particularly non-power users who may not understand the risks, but people can click through them. So that's why you see those categories up here. The last category that I'd just call out is hostile downloaders. So for us, that's defined as an application that basically downloads other PHA categories. So these categories are basically the scope of the trends and the case studies that we're going to be looking at today. So with that background in mind, let's dive into some of the high-level trends to get us started. So this is starting very broadly. The slide shows the percentage of devices that are seen with 1 or more PHA on them in the ecosystem. So we kind of define this as the Android healthiness of the ecosystem, and it's divided into 2 sections. You can see the healthiness for Google Play specifically, and then the yellow bar will show you the healthiness across the entire Android ecosystem. So looking at the trends for the first half of this year compared to last year, in 2017, we saw an average 0.82% of devices had one or more PHA in the entire ecosystem. And then in the first half of 2018, we've seen that come down a little bit to 0.72%. In terms of the trend for Google Play, as you can see, it's pretty similar to what we saw last year. Bottom line being, if you download apps exclusively from Google Play, you're basically 9 times less likely to have PHA put on your device compared to if you download apps from other sources. Still keeping at a really high level, although the overall trend for 2018 so far is good, we've seen the ecosystem become a little bit safer. It does vary by country that the device is in. So we've just pulled out 10 different countries to give you a bit of an idea of that variance. So for example, you can see the top two, the blue and the yellow line there, indicate that for India and Indonesia, you're more likely to get PHA on your device, and they're above the global average, compared to the bottom line in orange there indicates that in Japan, you're less likely, and it's lower than the global average. All right, so centering in on Google Play, what did we see as the top 10 PHA categories for the first half of this year? They're listed here in order of prevalence. So in other words, the most prevalent PHA category that we found on Google Play so far this year was click fraud. And I'll go into that in a little bit more detail in a second. Following click fraud was spyware, and then SMS fraud, which was one of those categories of mobile billing fraud that I mentioned earlier. This is a similar slide, but now we're showing the top 10 categories outside of Google Play. So as you can see, it's a bit different in terms of the dominance of different PHA categories. So this time, for the first half of the year, we saw backdoors as the prevalent PHA category, followed by hostile downloaders, and then privilege escalation. All right, I wanted to go into 4 specific trends with you today that we found interesting, that hopefully you will too. And the first one of those is SMS fraud. As you can see, this slide actually goes back to 2017, just to give you a bit of context for where we were heading into the year. So essentially, at the start of 2018, we were already at a spike in SMS fraud activity. So it's really been a big focus for Google Play Protect so far this year. In particular, we've seen PHA families in this category impacting the Southeast Asian region, and Maddie's actually going to give you the technical details for one of the primary families in that regard, which is Bread SMS, as well as run through Chamois, which has some of these SMS fraud-related behaviours as well. The second trend that I wanted to go through was hostile downloaders. So what was interesting is towards the end of last year, we'd luckily seen a nice big drop in the prevalence of hostile downloaders. That said, and that has been maintained throughout the first half of this year, which is great. But despite the fact that it's less prevalent, it's still a primary PHA category outside of Play. And so for that reason, we keep continuing to put resources into trying to counter this particular PHA category. In terms of why we think that drop has happened and how it's been maintained, there's a couple of factors that we think are impacting it. Some of those include the fact that we're now disallowing any kind of dynamic code download. We've also improved the ASOP detection support in both Android P and O. And then lastly, we've also removed the ability of hostile downloaders to install other apps. So in general, if there's a PHA on a device and it tries to install another app, we'll show the user a warning, regardless on that app, to try and warn them of the fact that we know this is coming from a PHA, you may want to be extra careful about what this is. But in the case of a known hostile downloader, we actually automatically block that download to try and stop the spread of this particular category. So we think those are the kind of factors which are leading into this trend. But if anyone else is looking into this area and has any other insights, we'd love to chat. The third trend we wanted to talk about was click fraud. Now, the data for here only goes back until December last year, and obviously looking at the slide, the trend looks pretty awful for the first half of the year, but that's actually mainly because we only began enforcement against click fraud in March of this year, so hence you see that big lovely spike going on there. Originally, we didn't consider click fraud to be PHA, And the main reason behind that is because of the actual limited user harm. And when I mentioned that definition at the beginning, usually our PHA categories focus in on that user harm aspect. But it became increasingly apparent that while click fraud may have limited user impact, it was having a really significant impact on advertising networks, and then by extension, all the businesses and companies that they represent, right? So we're having significant harm to a different type of group. And we decided that we couldn't keep ignoring that in our PHA categories. And when we did start enforcement in March, as you can see from that spike, click fraud really quickly became our top PHA category on Play. I think Maddie's going to be going into View SDK as a bit of an example of one of the families leading to this trend. The last trend that I wanted to highlight before I let Maddie delve into some of the actual technical details of families impacting these trends is phishing. I think phishing is a really interesting one, right? It's a really high impact threat, and so deservedly so, it's received a lot of press attention, both last year and that's continued into the first half of this year. But compared to the amount of press attention it gets, it's actually a really small threat on Google Play. You can see that last year, obviously we had a lot of spikes, but for the, pretty much continuously throughout the first half of the year, it's remained low. The interesting story for us about this is while we've managed to bring the prevalence of phishing down, there are still active phishing threats ongoing. And one example is a phishing family that's actually trying to penetrate Google Play that targets Turkish banks. So this is a good takeaway for us that when we're looking at these trends and deciding where to put resources and where to try and focus our efforts in fighting PHA, that it's important not to take our eye off categories just because we've managed to decrease their prevalence. Malware authors are continuously trying to improve and trying to evade those detection efforts, and this particular family that's targeting Turkish banks is a good example of that. We need to keep an eye out and keep trying to catch them before we see those trends spike up again. So with that kind of context in mind, I'll hand it over to Maddie to chat us through some of the examples.
Thanks, Kylie. So now that we sort of understand what's the most current data of impact happening in the ecosystem, let's talk into some of the most current techniques that the biggest families are using in order to have that big impact. So the first family we're going to talk about is called Chamois. Chamois is a botnet that is pretty complicated, complex, and its whole purpose is to do different types of ad fraud, premium SMS fraud, or install fraud. So when Kylie told us that for 2018, so far the biggest PHA category in the off-market space is backdoor, that is largely because of the Chamois botnet. And so prior to March 2017, Chamois really pushed and tried to infiltrate Google Play. After a lot of different defenses that we'd put in place and things like that, they moved off of Google Play and then reevaluated, re-strategized, and decided to try and penetrate the side-loaded off-market area of Android. So we began detecting Chamois in mid-2016. At that point, as I said, it was Google Play, and it's still ongoing, but now it's completely off of Google Play. So for all of these families we go into, I will give you a sample of the family via the SHA-256 digest, and I went ahead and put a short URL to the virus total link in case you're trying to follow along. So here's a first overview of what Chamois is. So this image came from a blog post we did on Chamois back in 2017. So this was when we had just a first couple of variants and we had worked to push it off of Google Play. It still is overall the same though. Chamois is 4 stages, the first being the APK, the last being a jar of the payloads. So across that, the different variants we're going to go into today and how they continue to evolve is how they get or where they do each of these different stages in the functionality, but overall, the functionality for each of these stages has stayed the same. So we see the APK, that dynamically drops and unpacks stage 2, which is a jar. Stage 2's purpose is to decrypt and drop stage 3, which is an ELF or native code within the Android application. Then stage 3 unpacks the final payload and drops that and starts it running. So the very first variant we saw in late 2016 sort of goes along what I stated before of those 4 stages. So first we saw the last 3 stages, stages 2 through stages 4, were all packed and encrypted in different files in the assets folder of the APK. So stage 1 starts, runs general Java code, which unpacks, drops the jar. Each of these final 3 files all had dynamically generated file names. So for example, stage 2 was always assets/32, either lowercase or numerical characters. So I have the regex listed of what their common file names were for variant 1. So variant 1's first payload, what they attempted to do was general add fraud and install fraud. What I mean by install fraud is if you think of a payload, for this type of botnet, their whole purpose is monetization. So they're trying to come up with different ways to monetize the fact that they're on all these different devices. So ad fraud's pretty general. We hear about it a lot, just different ways to defraud advertising networks. But install fraud means, hey, we're willing to sell you the fact that we're installed on all these devices and we'll install your applications as a developer also on these phones. So that ties into sort of that hostile downloader category that Kylie was talking about before as well. So variant 1 had an interesting but simple string obfuscation technique. So it was used in both stage 1 and the stage 2 jar that we saw for variant 1. And so what you would see is there was one class within both stage 1 and stage 2 that just had these, what looks like an integer array in there. But there were no strings at all in the classes. And then you would see that this integer array was used in this one function. So the next thing you would see is how was this function called? And it was pretty simple. They would call this function with 2 integers. The first integer, when you take a quick look at that function, is the index of the value to start at in the array. Then the next integer is the length, the number of values from the array to read. So in this case, A, 29, 8 would give us these 8 integer values, 111, 110, 67. And then it was as simple as that is the decimal representation of the ASCII value for the string. So this string was simply on create. So probably one of the simplest obfuscation methods that most of us in this room can think of, but it was successful in that you could no longer just scan the APK looking for strings. You had to write a tool in order to find those strings and be able to put it in your automated detection systems. Then we moved into stage 2 in the later half of variant 2, in the later half of 2016. For variant 2, all of the stages stayed exactly the same. They still used those 3 different files that were stored in the APK's assets folder. They would drop them dynamically, use the same unpacking and decryption for each of the different stages. But we saw the payload change. Now instead of just doing ad fraud and install fraud, they came up with a new monetization mechanism. So this time it was premium SMS fraud. So to take a step back, premium SMS fraud in Western Europe and the US, for those people who are here, it's not as common of a way to pay, but what it means is that if you send a text message to this short code number like 5555, it will charge your mobile bill a specified amount. So you're allowed to send premium SMS messages, but you're not allowed to do it without user consent. So that's what makes it fraud. And so Chamois would do this in that they would do this behind the scenes, send all these premium SMS messages, and then have this charged to the user's bill. And so they did it in a sophisticated way because the Google Play Protect Android security team had already been building in a lot of different mechanisms to protect users from premium SMS fraud, such as requiring a specific permission, and also whenever the phone detected that an app was trying to send an SMS message to a short code number that was likely premium, it would pop up a dialog. So what Chamois did was it tried to find rooted phones. And on those rooted phones, it would try to install itself so that it could run as the system user or the phone user ID. Both of those on Android are privileged user IDs. And so once it did that, then it would do different types of bypasses to make the phone believe it had the the SMS permission, and also, oh no, the user has told us that we don't want to show the dialogues for premium SMS messages. So that was the interesting changes for variant 2. That one basically was eradicated in March 2017. If you look up Google Chamois, you'll see a blog post about it that also goes into more details. Then they went dormant for a few months, because this was after we had pushed them off of Play. Before that, we hadn't seen them in the off market that much. It was a constant battle to just push them off Play. So then in November 2017, we see them start to come back. But they've changed quite a bit. And so this time they're purely targeting the off-market or side-loaded ecosystem part of Android. So not even attempting to get back on Play. So what we see as the stages go, and why this was not immediately clear to us that it was related to Chamois off the bat, was that, yes, stage 1 was an APK. But this time we didn't see the same assets files stored in the APK as we had seen previously. Those random generated characters under assets had been a pretty clear and obvious thing that something was out of the ordinary. Instead, they moved stage 2. Instead of dropping it as a jar, they just included that Java code in the APK, but it was highly obfuscated with lots of random class name strings and things like that. So what that also, now stage 3, which is where a lot of sort of the meat of this variant came in, was now no longer dropped, but was included as a static ELF within the APK. If you haven't analyzed many Android apps thus far, developers can choose to include compiled C or C++ code in their applications, even though we generally think of them usually written in Java or Kotlin as applications. So they included this ELF. It usually lived in the path lib/whatever CPU it had been compiled for, usually Army ABI, which is the Android sort of keyword term for generic ARM. But we also saw it for ARM v7 and ARM 64, as well as x86. And then it had a randomly generated name, which was usually lib, and then 5 to 8 lowercase letters, .so. So I'm going to take a step back to talk about these randomly generated characters. I think it's important that whenever you see lots of samples of a similar family, if they're able to generate all these random file names and random strings and class names, that's a really strong signal that it's either being distributed to people in the form of source code, or the malware developers have lots of resources and have created an automated pipeline that generates all these different samples, and thus obviously are not generating all the random names by hand. So the key aspect of this ELF, which required quite a bit of reverse engineering, was that it didn't look the same as the previous ELFs. Instead, there was a lot of anti-analysis, anti-debugging, and decryption around it so that it didn't look right when you first analyzed it. And so what this was is an anti-analysis native library in Android that I have named Wedding Cake, which was one of the most complex native libraries, or complex anti-analysis native libraries we've seen because of the variety of different techniques they used. If you're interested in that, I did a Black Hat talk this year, as well as wrote a paper for Virus Bulletin that was published a few weeks ago. So if you're interested in the types of anti-analysis techniques being used today for Android, go ahead and check that out. So once I got through all of those layers of anti-analysis that I hadn't seen before, the way that I knew it was finally Chamois was that it had the exact same functionality hiding under those layers of Wedding Cake as the previous stage 3 for Chamois did. So again, now we found that its whole functionality was to drop stage 4, the payload. This wasn't working, though, in any of the dynamic analysis pipelines, and why it was tougher to figure out and required this reverse engineering is because they now included all of these anti-analysis and obfuscation techniques. But ultimately, it drops the payload as well, which they sort of backed off from the SMS fraud payload and moved back into more different types of ad fraud and install fraud. So from about February to June 2018, built all these detections for Wedding wedding cake preventions, different things like that for this new variant, and I started putting out information about wedding cake. Then I presented at Black Hat, and we saw variant 4 come out after talking about it. And so what they changed here was they left stage 1 and 2 the same. They generally left stage 4, their payload, the same, but they targeted stage 3, where wedding cake had lived. So what was interesting leading up to what I would say the true boundary with variant 4 was we were able to watch all the different versions of chamois apps coming in. And what I could see first is that it seemed that the malware developers were trying to test if we had Yara rules in place or how are we catching them. So we could watch in both the Java code as the Yara how they were trying to move different things around, put constants in different places, probably trying to test for those exact types of signatures for detection. So instead, they decided to pull the ELF completely out of the APK for variant 4. So what they did now is they base 64 encoded the entirety of the ELF, and then put those base 64 encoded strings in the APK. The Java code of stage 2 then decodes each of those strings that are a portion of the ELF, and then concatenates them all together, writes them to the file to then drop the ELF. So what that looks like is a little like this. The new version of Chamois, we saw all of these base 64 encoded strings in an array. Here, I just happened to pull out, value 56, but they often had hundreds of them. And so then they just had simple code that concatenates them all together. One of the interesting parts here is where they build the path to drop it. It's again randomly generated strings for the directory and then the actual file where they would like to drop the ELF. But what's interesting is they do append a period before the folder name of KDUSIP to make that a hidden folder if you were looking at it. So that was Chamois, one of the biggest botnets we've seen in the Android ecosystem and the big contributing factor in the off-market or side-loaded space to that backdoor category. So now let's switch to Play. What are we tackling, fighting, preventing on Google Play? And that's this SMS fraud family, as Kylie alluded to. We call it red SMS because it sends SMS. So it did originally start as SMS, but then as we were getting, stronger and stronger detections in place, prevention, they weren't having the same surface area, or they weren't being able to distribute themselves as effectively. They decided to innovate and do some toll fraud as well. So this has been about 2016 to present, and again, here's a sample and a virus total link. But one of the key aspects of Bread SMS that is fascinating and sort of similar to Chamois is how resourced it is, because it is rapidly evolving with many variants. So that means you have to be very deliberate with how you use analysis resources, how you use detection and prevention resources, because you know that they're well-resourced and able to find so many variants. So I'm not going to be able to go through all of them today, but I'm going to touch on some of the most interesting SMS fraud techniques that their variants have used. And so when you think about it, SMS fraud is just sending a text message. Sending a text message, there's only 3 or 4 Android API calls that allow you to do that. Shouldn't that be pretty easy to detect? Because they have to do it in one of these 4 ways. However, that's where sort of the creativity and where us as defenders really have to work, and where malware authors are constantly trying to evolve, is because you're trying to come up with new ways to send the SMS and ultimately call that API call without being detected. So one of the first ways they do that is with a simple splash screen. So their goal of their splash screen is 1, to prevent the automated dynamic analysis catching them. 2, they try and fake policy compliance. It's super small on their screenshot, as probably intended, but they have in English at the top, terms and conditions, and then some tie underneath it. So what I mean by fake policy compliance is you're allowed to send premium SMS messages on Android as long as it's fully disclosed the price and the number to the user and the user consents. So this is probably their attempt to make us think, oh, something in tie, they're probably disclosing this. But the other aspect of this is that they dynamically update the content in their terms and conditions based on the C2 and where you're checking in. So this is a form of the cloaking they use that we'll get into. So sometimes it says, hey, click the button if you want to continue to the app. And other times they have a real disclosure when they think it's probably us who are trying to review the apps. So the key cloaking that they began to use is only sending or performing the fraudulent behavior of sending the SMS message when you're on a certain mobile carrier. Because based on how SMS fraud works, when you send the SMS message, that sort of provider of the premium SMS number has to have the relationship with your carrier to be able to charge your carrier's bill. Bread SMS targets exclusively Southeast Asia and almost predominantly Thailand, so it's not really worth it to them to try and to accidentally be detected if they're running on, let's say, a US, Western Europe, or Brazilian's phone, because they're not actually going to be able to make money that way. So we'll talk a little bit about how they do that check. So they send a command and control request that says, hey, only perform the fraudulent sending the fraudulent SMS message if the phone is on one of these carriers. Otherwise, that button will now just start the main activity and it won't do any of the sending. So what that actually looks like is we'll see the example C2 command and control request URL up here on the top left, and then the response that the app received is the JSON on the bottom left. And on the right here is the code, which we'll go through and make larger. So the very first thing that happen is they get the user's SIM operator or their mobile carrier using that code. That is then passed to the HTTP request that is sent to the command and control server. You see that as in this example, code equals 31026. The app then receives back the JSON response and parses that. So based on that, they've now set the, they first get the contents that are supposed to be set in that splash screen text. So in this case, they're going to say, here are all the pictures you need about happiness, beauty, etc., with our most sincere service to provide you with the most robust resources. So that's where I mean they change those terms and conditions based on whatever the service tells them to say. The next thing they do is they also set what the button text is going to say. Here, it's that content. And now they check what were the IMEIs, they're not actual IMEIs, but what is the carrier sent back in the response? It's here under the variable they use IMEI. So they get all of those, and if the user's carrier was in those values, so for us it was not, if you look at 31026 is not included in these three carrier codes that were sent back from the server. Then, and only when the value is in there, do they actually send the SMS. Otherwise, they do this top if statement of just starting the main activity and not trying to send the premium SMS. So the next variant is all of that code before for variant 1 was included in the application. So we could still see the HTML and all of the code to portray the splash screen. Now they moved into a web view. The reason behind that is now the only code you have to have in the application is what the application wants to do to interact with the web view page. And so they can dynamically generate, allocate everything within the web view otherwise. So for example, we have this HTTP request URL that goes to the command and control server. You see an operated code, the name of the app, and some device ID, which we dead beefed out. Then you receive this response. So the very first thing you see is the on click, and it says we're going to run sub. You see that the sub is the JavaScript down here at the bottom. But first, let's talk through what each of these variables are. Because they've hidden the premium SMS code arguments in the HTML. these are, set as variables, but not actually displayed to the user. It's just saying short code equals this phone number, and keyword is this contents. The next thing we see is some references to Android APIs to send a text message. If you've ever used Java and heard of reflection, that's another way to call Java or Android APIs without having to call the function itself. Instead, you send the strings that then tell the virtual machine, hey, you're going to find this method and run it. So that's all the arguments they need here to do that for send text message. So therefore, now we saw at the top that this HTML said when the button is pressed, run this script. We can see what the script's values were. The first lines of code were all to load those variables we just talked about. And now here we see that they're actually calling a function to send the SMS message by having these hidden values encoded in the HTML. And so finally, what that looks like, there's all the variables for you. They're going to call the Android API method, send text message with the arguments of this phone number and that contents of the text message, which would ultimately charge the user. So that wasn't enough. We then saw them rotate to a new variant quickly again. And this time trying to come up with a new way to call send text message without being detected. So we've seen it where they do it straight in the Android API calls. We've seen it through calling from a JavaScript in a web view, and now they move to that native code. So what we saw in the Java code of the APK is they declared this native method saying, hey, this is actually going to run in C or C++ in compiled code. They left it still named quite well for us, so that was helpful. So we have this native send method, which takes two strings that's declared, and then we see that it's called in the APK as this bottom line here. I know it's a little small, but hopefully you can still read and get the gist of it. This is a screenshot of the IDA of the native library that was included in the APK. What we see is they then call send text message in the way that the JNI or Java native interface, how you interact between Java and native code. They call send text message with the two arguments of the short code and the contents. So that was a whirlwind deep dive into 3 of the variants of one of the most impactful families on Google Play and one of the large contributors to the SMS fraud PHA category that we're seeing in the first half of 2018. So now that we've talked about off-market side-loaded apps, Google Play, now we're going to get into something a little different, the pre-installed problem. Not the first one to come up here and say that's the thing. So Casaloon is one of those that has been pre-installed before. So it is a hostile downloader, so that category that Kylie was talking about earlier. It is not really off-market side-loaded so it is considered off-market or side-loaded because it's not Google Play, but its distribution mechanism is pre-installed. So it was detected in November 2017 and basically sort of fell off in March 2018, largely because of an analysis and collaboration we did with Avast, and Avast published a nice blog post about that if you're interested in reading more specifically about this family. So, overview of Casaloon. It's 2 stages. First stage is pre-installed on generally low-end or non-certified Android devices. So that stage 1 can come in 2 different types of variants. One is just a pre-installed application on the system partition, just general bloatware that you can see on some of the lower-end or non-certified devices. Variant 2 is there is a package or application that is critical to the Android platform. It's in AOSP, the Android open source project, and it's called System UI, doing, as the name suggests, a lot of the UI for the system of Android. And so what they did there is they actually modified System UI to be this stage 1 dropper for some of this hostile downloading and ad networks. So they both have the same exact functionality, just the way it was packaged and distributed is slightly different. Then stage 2, which is dropped by stage 1, ultimately displays ads and installs other applications, and that's how it gets the PHA category of hostile downloader. So, as we said, it's pre-installed for stage 1. That means it's on the system partition, or in this modified system UI, which is also on the system partition. Both of these stage 1s register a Wi-Fi state change receiver, meaning that anytime you either connect or disconnect from Wi-Fi, an action is sent to these applications that allows them to execute. Most of the key behavior that we're going to talk about is in 2 classes that they have named Wi-Fi broad or KeyGuard broad. These have nothing to do with the normally included Wi-Fi or KeyGuard applications. They chose to name them that to probably not raise a lot of suspicion. So the key here, though, that was interesting, is the behavior that's in here and ultimately leads to the fraudulent behavior of dropping stage 2 only occurs if you are not in China. It does this check of code right here to get your locale and make sure you're connected. But if you have a locale of China, they do not execute and they go dormant on the phone. So once they've done that check, they've decided you're connected to the internet and you are not in China, they run this code that's called check update. Check update then connects to a subdomain or the domain of costloon.com and downloads a XML file. This XML file gives all of the configuration settings necessary for stage 2 and the payload to operate. So the version number changes for the XML file over different versions, as well as the subdomain of Costloon. So this is what the response to the call to get that version.xml file looks like. So some of the key aspects here is 1, the version. This is saying, hey, this is the version of the config file, so the app will actually only update the values that it knows as its configuration settings if this is a later version than a version it's seen previously. This is now the URL where they download the stage 2 application from. So they download it. Since they're running as system, they were able to call pm install-r command to do the install of stage 2 APK. Package is usually the name of that stage 2 APK as well. These startup values were interesting. So what these startup values are is they are going to set a preference within the stage 1 application that says every time the phone boots up, you're going to start these services. These services are usually living in the stage 2 application. So it's the way that that stage 1 system pre-installed application is able to ensure the longevity and the lifeline of the stage 2 application that gets installed. Lastly, they do a couple of different types of whitelisting. So if they have the ability to send board, device, and model values back in this reject variable value, and if the phone's values matches the ones of reject, they also will not run. The final interesting check they do is they send an HTTP request to these CDNs that are at getip.php. This returns an IP as well as a timestamp. What it looks like is that this is a second localization check. Because it's a CDN, that means the server is going to be based in different parts of the world and respond to you based on where you're trying to connect from. And so they use that to check, hey, is this a place we still want to run from? So now that we've gone through stage 1, we passed all the checks. Yay, us, we download stage 2. So stage 2 almost always had these different package names trying to pretend to be Google products, saying e-music service, e-play service, sometimes adding some integers in there, and every once in a while spelling Google wrong. And this was much more obfuscated than stage 1. Generally, stage 1 was not obfuscated at all. All of the strings were included in one class. And then they had just about all of their functionality in a single service called back service. So what they do is, this is the service that ultimately the stage 1 was trying to start up with those startup values. And once it's started, it uses a screen observer object from Android APIs to start and stop the service based on when the screen is on. This is used to show ads and sort of see, we're only showing ads when the screen is on, and thus you should pay us more for their monetization ad fraud. Lastly, it does drop a jar. That's the ad library. Yeah. So the final family we're going to go into is one of these new examples of click fraud. As Kylie mentioned, we only started enforcing, detecting, preventing on-click fraud in March 2019. So this was one of the first families and one of the families that sort of pushed that decision to start enforcing. And so we're going to talk about how they do that. So we detected it before we started enforcing on it back in February 2018. It's only on side loaded. We haven't found this one on Google Play. So the way it works is you have an APK. An APK then drops a jar as it's running. And this jar contains the class com.view.sdk, hence the name we gave it, .star, usually something that's pro-guarded, so single letter. The jar is usually named 9digits.jar. So the way that it does click fraud is it creates an invisible web view that show ads. So the user can't see them, can't be annoyed, can't report them, can't delete the app, but then it uses JavaScript to inject clicks on it. So that makes it look like to the ad networks that a human is interacting with the ads you're showing, and thus they should pay the person that has that advertising ID. So the way this works is that in the WebView client, the invisible one, where they're showing all of the ads, in the on-page finished function, which is as it describes an Android API for WebView that runs whenever the page is finished loading, it downloads JavaScript. That JavaScript is then run. So it usually was downloaded from this link. What that JavaScript that's downloaded looked like was this, really hidden name click.js ad. So it combs through the web view or that web page, looking for any items that are in the web page that have the element name ad area. It then tries to calculate with a little random wiggle room to hopefully not trigger different types of click fraud detection mechanisms where it wants to click. Once it does that, it then calls this foreign SDK.adsClick function. Foreign SDK is the name, what they gave the name of the JavaScript interface when they were creating this web view. So if you haven't interacted with web views, that often you might be looking around for a class named Foreign SDK, but it's actually this other class, ComView SDK ATA, that they happen to name Foreign SDK. So then you can take a look there. And ultimately what that function does is it checks the proposed XY click values that function sent in against the screen size and the density. It then checks the other configuration settings such as how quickly am I clicking? How many times have I clicked? And that's ways that they try to hide themselves from advertising networks that are trying to detect fraud as well. And ultimately, it uses the API call dispatch touch event to do the click. So with that, I hope it was interesting. We went through all of the malware trends or PHA trends for the first half of 2018 and then tried to really do a deep dive into the most modern or current techniques that malware authors are using to become impactful, to become prevalent, and how they evolve and sort of vary their techniques as well.
So a couple of key takeaways, well, I guess two more broad ones, is I've now discovered that even if you lock that door, it doesn't stay closed, by the way. And my second key takeaway for you for general life is apparently weeks after having a cold, you can still cough like crazy. So sorry about that. But in terms of actual malware detection, one of our key takeaways we've really kind of honed in on over the last 6 months at Google is that focused detection efforts can really have a big impact on PHA. And I think one of the categories where we've seen that is hostile downloaders and the work that was done last year. And by highlighting some of the categories that we see as being the most prominent and prevalent, in the Android ecosystem. We're hoping that we can really encourage others that if you're seeing similar trends, please come to us, come work with us, let's collaborate. When we all focus in on these categories, it's when we can have the best impact. The second one is the fact that we, always need to suspect cloaking and obfuscation. Luckily, Maddie is a little cynical and already does that by trade. But I think all the examples that she's shown today really highlight that, right? All the impactful malware families that we see tend to use combinations of those techniques to try and evade detections, and they're constantly changing the way they use those techniques. So we need to keep on the lookout for that. The last lessons learned from us is don't be complacent. Always consider a missing variant. When we've been looking at these impactful families, we see that most of them are really well-resourced. And that means that they actually have the capability to evolve rapidly, change things. I think Bread SMS is a really good example of that. With the money they're bringing in, they can hire more and more engineers to change the code more quickly. Every time we put in detection mechanisms, they try and work them out, they try and evade them. So for us as a community, I think that means we need to constantly suspect that there's a variant we're missing. So whenever you think that you have a family solved, that you have the right detection mechanism, go and broaden your search, look a little bit different for slightly different samples and see if there's something we're missing. Just saying. We think fighting PHA is brilliant. If you think it's brilliant too, come chat. And here's some more resources. So as I said, those PHA definitions are available online. We also have last year's Android Year in Review report. And in general, if you see something that you suspect is PHA, here's my email. Please feel free to get in touch. We'd love to hear from you.
And so thank you all for... What? Oh, yeah.
sorry.
Yeah, so thank you all for coming after lunch. The two of us are the ones up here presenting, but all of this work really has been, as always, a collaboration. There's many different people behind the scenes that help us obviously analyze, calculate, all these different things. So, yeah, thank you. Questions?
Pessoal, temos uns 5 minutinhos só para perguntas, tá? Aí quem quiser, só levantar a mão.
You told that some malwares are constantly checking where you are right now, right? Why is that? Why do you think that they don't attack on China's soil, for example?
So I think one, you need to... So I'm not a lawyer, and I'm also obviously making some guesses of what I think the answer is. But I think based on where the developers are in the world and where they may not want to target their own people. There's also the checking as in Bread SMS that you don't want to, it's not worth executing the bad behavior if the person is not in the area of the world where you can make money. I think there's also... you may choose, if you're a malware developer, to execute bad stuff in areas where you don't think it's as likely that if you're found, you will be prosecuted or put in jail. So I think all of these sort of come into the cost risk or the risk benefit decision for malware authors. And, the world is pretty dispersed in how we treat, find, and able to detect or fight malware.
I think the only thing I'd add to that is there are obviously some types of PHA that deliberately try and target specific groups, right? So I think phishing is something that comes to mind that can often be more targeted. And in that case, it doesn't really make sense to broadly target everybody when there's really a select group that you're going after.
Yeah, makes sense.
Can you talk about the tools you use to do this kind of analysis?
So we can't talk about the proprietary tools that Google uses to detect, but for most of my reverse engineering, I still use IDA-Pro or the JEB decompiler, as well as then internal tools we've developed. So yeah, if you are a reverser, have used IDA or Binary Ninja or any other disassembler, I started with Object Dump, and then before I could get a job to pay for a JEB decompiler license, I used the JADEX decompiler for Java code or Android applications, which is also free.
Thank you.
Hi, congratulations for the presentation. Two questions. First, do you guys try to work with law enforcement agencies in parallel to try to find these guys? And the second question, what are the strategies against side-loaded PAJ because you guys can't drop it from the Google Play because it's not there, so how can you mitigate those threats?
So I will take the side-loaded question first. So Google Play Protect is built into Android operating system, and if a user consents, then our goal is to still protect those users even if they're choosing not to download their applications from Play, because they've said we want GPP protection. And so I think that's especially important because the accessibility to Google Play also and how much is dependent across the world based on what is your infrastructure. How much does downloading an app cost you and things like that. And so I think I personally care, and I work almost exclusively on the non-Google Play problem, is because there are so many other people around the world who they have a lot of reasons that mean maybe disadvantaged in different ways that make it side loading a better option for them for downloading apps. And then
I get the first question. So I guess I'd say more broadly, at Google Play Protect, we're obviously focused on what we can impact, right? And so for us, one of the primary mechanisms we use to protect users is to show them a warning. So the whole idea is we're not trying to be the gatekeepers to what people can and can't have on their device. I mentioned earlier at the start of the presentation about categories we have related to apps that can modify security settings, right? And there are cases where we think that's PHA because in general it's risky, but there are some users who want it. So when we show warnings, usually users can click through them if they choose to. So step one is that is our primary mechanism that we use to try and detect and protect users. Obviously, as Google, if we receive a legal request for information and it complies with the legal requirements of that country, then obviously we're under a lawful obligation to provide it. And as I said before, we're always open to collaboration with the industry when it comes to trying to fight PHA. But our first focus is on thinking about how we can protect it in the ecosystem we control, and that is through warnings.